Hey team, welcome to the numbers game. I'm Coach T, and in this tutorial we're going to be using the definition of convergence to prove that our sequence does not converge. Now before we get started, make sure to subscribe to the channel for notifications on more math tutorials. Alright, now let's take a look at this example. Our example says let b sub j equal -1 raised to j, where j is a natural number. We're going to prove that this sequence does not converge. Before we get into our proof, let's go over the convergence definition. It says a sequence a sub n, where n is a natural number, converges to a if the limit as n approaches infinity of the sequence a sub n equals a. Or in other words, for all epsilon greater than 0, there exists a natural number n such that the absolute value of the sequence a sub n minus a is less than epsilon. Now, I'll mainly reference the last piece of this definition during the execution of our proof. I won't really use limits to prove this particular example, so I'm going to reformat the definition so we can focus on the absolute value of a sub n minus a less than epsilon piece. Alright, so now that we've reviewed the definition of convergence of a sequence, we'll start our proof. The first thing that we'll do is suppose our sequence converges to a number alpha. Now we'll set epsilon equal to a half. Then by definition of convergence, there exists a natural number n such that if j is greater than n, then the absolute value of b sub j minus alpha is less than epsilon, which equals a half. Now I'm going to go over that again so that you all understand the correlation between what we just wrote and the convergence definition. So again, suppose that our sequence b sub j converges to a number alpha. We're going to set epsilon equal to a half. And by definition, if our sequence b sub j converges to a number alpha, then there must exist a natural number n such that if j is greater than n, then the absolute value of b sub j minus alpha is less than epsilon. And of course, we've already chosen epsilon as a half. Now moving on, we see that the absolute value of b sub j minus the next number in the sequence, which is b sub j plus 1. This can expand to the absolute value of b sub j minus alpha plus alpha minus b sub j plus 1. And this is because if you recall, in our example, we're given b sub j as -1 raised to j, where j is a natural number. So this means that b sub j is always alternating between negative and positive. For example, -1 raised to 1 is -1, -1 raised to 2 is 1, -1 raised to 3 is -1, and it's alternating between negative and positive. So at this point we have two terms, and I'm going to split the absolute value. So that's the absolute value of b sub j minus alpha plus the absolute value of alpha minus b sub j plus 1. So keep in mind, earlier in the proof we said that the absolute value of b sub j minus alpha is less than epsilon. So that means that this piece here is less than epsilon plus epsilon. Earlier in the proof we also set epsilon equal to a half, so that's a half plus a half, and this just equals 1. On the other hand, the absolute value of b sub j minus b sub j plus 1 equals the absolute value of -1 raised to j minus -1 raised to j plus 1, and this equals 2. But we see that we have a contradiction. If the absolute value of b sub j minus b sub j plus 1 is 2, and earlier we showed that that's less than epsilon plus epsilon, which ultimately equals 1, then we see that 2 is less than 1 is a contradiction. So we've proved by contradiction the sequence does not converge. And there you have it. We've proven that our sequence does not converge. If this video was helpful for you, give it a thumbs up, like the video, drop a comment down below, and subscribe to the channel for notifications on more math tutorials. I'm Coach T, and thanks for watching the numbers game.